Okay. Marshall's finally ready. Okay, so we have discussed Newton's laws. First law says if I'm in motion, which I am, I resist a change in that motion unless there's a what kind of force? What's the specific term I'm looking for? A net force, thank you. So if there's a net force, I can change motion. Second law says this is how much force is required to change motion. Third law says for every action force, there's an equal and opposite reaction force. And just as a follow-up to that, if I push down on this desk, how do I know that the desk is pushing up on me with an equal and opposite force? No, it's not that I'm not moving, it's that I'm not what? Accelerating. Okay, you've got to have that mind frame, right? It's not just that I'm not moving if there are balanced forces, I'm not accelerating. So I know there has to be an equal and opposite force pushing on my hand with the same force that I'm pushing because my hand's not accelerating. Okay? And that's a really profound thing when you realize that that has to be the case. Okay, your voices carry all the way up here and it really distracts me. So
we're just trying to get acceleration.
Yeah.
The accelerator, like it's something, and it's like the acceleration slowing down to hit an object, right?
Okay, so acceleration describes both speeding up and slowing down, right?
Right.
Okay, so what's your specific question then?
Okay, but like if you hit a wall.
Uh-huh.
And
so,
it like pushes back, but you still are like
okay.
slowing down.
So and we conveniently ignore that instant of time when you slow down. Okay? So if I push my hand down there, there's going to be an instant in time where the force on me must be greater than the force that I'm pushing down with because my hand slows down, right? So that force pushing up on me initially, the table would be pushing up with a greater force than what I was pushing down with. But eventually my hand comes to rest and then there is no more acceleration. So if I'm just pushing down, the forces have to be balanced because I'm not accelerating at that point.
Okay, so your velocity is going this way, you're accelerating this way. Once you hit the wall, you're accelerating this way, but your velocity is still this way?
Yes. Yes, it slows down very quickly though, doesn't it?
Yeah.
Okay. It goes almost instantly to zero. So, okay, so I'm sorry I yelled at you because you were discussing physics.
I'm willing to cry a little bit.
Don't worry about it. You shouldn't. Oh, dang. Why did that stop? Okay, so the other thing to think about that is what happens to the force that, if I increase the force that I'm pushing down on the table with, does it make sense that the table also increases its force back up on me? And that's extraordinary because this is an inanimate object. It can't think, oh, I need to push back up with a greater force because they're pushing down on me with a greater force. It just happens that this inanimate object changes the force with which it's pushing back on you. And I always thought that that was kind of strange to think about because it's an inanimate object. Okay, so now we need to talk about some specific forces. And one thing most people that don't know a whole lot about physics don't realize is that weight is actually a force. Okay, weight is actually a force. Earth exerts a force of gravity on all objects near the surface of the Earth, directed towards the center of the Earth. And as a force, gravity can cause an acceleration, the acceleration due to gravity. And we're already aware that in the absence of other forces, the acceleration caused by gravity is how much?
Negative 9.8 meters per second.
Negative 9.8 meters per second squared. Okay? Now, one of the things that just doesn't really occur to us then is that while we are being accelerated towards the center of the Earth by this force, the thing that doesn't occur to us is it doesn't seem like we're being accelerated towards the center of the Earth because the normal force of the Earth pushing back up on us has to be equal to that force, right? The normal force has to be equal to that force. Otherwise, we would be accelerating. But we have to be aware that that force due to gravity is still always present. If we were to just draw a free body diagram of that, we would know that the force due to gravity is balanced by the normal force. You don't have to draw that, but you're aware of that. And if we apply Newton's second law, the force related to this acceleration, the net force that's causing this acceleration, is F equals ma. Okay? Except we're going to say F equals mg because it's a specific acceleration, right? It's not just any acceleration. It's the acceleration due to gravity. And Newton's second law says that the force that's causing that acceleration is mass times the acceleration due to gravity. So we have to be mindful again that mass and weight are not the same thing. Mass is the amount of stuff that I have in me, right? And that doesn't change no matter where I am. If I'm here, if I'm on the moon, if I'm on Jupiter, oh, by the way, there's an amazing planetary, who was talking about that last time? Was that somebody in here that was talking about the planetary conjunction? Maybe that was in one of my other classes. Jupiter and Saturn are going to align near the end of December in almost perfect closeness. If you look at it with a pair of binoculars, it'll look like they're a double planet. And it's the first time it's happened in over 800 years. So it's a fairly rare event. But anyway, if I'm on Jupiter or I'm on Saturn or if I'm in the middle of space, my mass is the same, right? But if I apply the force due to gravity on my mass, then that is my weight. And people don't realize that if I apply the force due to gravity to my mass, that force and weight are the same thing. Force is, or weight is a force. And this is also called the weight of an object then. Okay, so please burn it into your brain. Your weight is your mass times the acceleration due to gravity. Now, you may think your weight is in pounds, okay? Well, it is in pounds, but realize that pounds is also a force, okay? Pounds is a force. Weight is a force in general. It doesn't matter whether you measure it in pounds or in newtons, it is a force. But in the English system, we also have a different acceleration due to gravity. In the SI system, the acceleration due to gravity is negative 9.8 meters per second squared. Does anybody know what the acceleration due to gravity is in the English system?
Yeah, because it looks like one.
Okay, what do we usually measure distances in the English system? Less than that. Feet. Okay, so it's going to be 32 feet per second squared. Okay, it's the same thing. It would be negative, yeah. So negative 32 feet per second squared. Okay, so if you're more interested in English units than SI units or metric units, but we have to do everything in metric units. So If I calculate things in feet per second squared, though, then the unit of force in the English system becomes the pound. And it's not really that difficult of a concept. It's just that we don't normally recall being told that our weight is actually a force. Okay, so your weight is a force, and it's the force due to gravity on your mass. So gravity doesn't disappear when an object is at rest on the surface. This means another force must be balancing the gravity, or the object would be accelerating. Not just moving, it would be accelerating. When a contact force acts perpendicularly to a surface to support an object, we say this supportive upward force is called the normal force, good, or just simply the normal. Okay? I might not always call it the normal force, I might just call it the normal. So, we have a problem here. A friend has given you a box of mass 10 kilograms. The box is resting on a smooth. Anytime you hear me say that something is on a smooth surface, that's code for frictionless. Okay? A smooth horizontal surface. Determine the weight of the box and the normal force exerted on it by the table. Okay, so I want to determine the weight of the box, and I always start my force problems with the free body diagram and what forces are acting on my box. What forces are acting on my box? Come on, guys. What forces are acting on my box? Thank you. And that equals mg. And what force is pushing up? The normal force. Force normal. Okay? It's not accelerating, so I know these things have to be balanced. And I can say the net force then. I only have two choices. If it's not accelerating, my net force has to be 0 newtons. If it is accelerating, my force has to be ma, right? But this is 0 newtons. And then this is going to equal, since I've got a force in the downward direction that's pulling down and a force that's balancing that pushing up, it doesn't really matter in my sum of forces which one goes first. I could say mg minus the normal force if I wanted to. And then I come up with mg equals the normal force. Okay? Now, I didn't entirely necessarily need to do this, but I have to be able to show, you have to be able to show me in some kind of a way that involves a formula and substitution into the formula what's going on here. And it says determine the weight of the box and the normal force. So now you've told me that whatever these two things are, they have to be equal to each other. But we have a mass, so we can go ahead and make this calculation, 10.0 kilograms. And what's the acceleration due to gravity? 9.8 meters per second squared. And again, when we use gravity in a force setting, we don't put the negative sign there because our math will take care of that for us. Okay, our net force equation will take care of assigning the negative value, and we end up with 98 newtons. Okay? So just to give you an idea of how many pounds this is, since I've said that pounds and weight or in force are the same thing, or they're both weight. Somebody look up newtons to pounds on your phone and see what the conversion factor is. We want to convert newtons to pounds. So I need a conversion factor. So newtons to pounds, or pounds to newtons, it doesn't matter.
Says the 1 Newton is 0.2248 pounds.
Okay, so 1 Newton is 0.2248 pounds. What if I go the other way? So I could do this either way, right? Since I want to get rid of newtons, I'll put that in my denominator, and I want to keep pounds, I'll put that in my numerator. What if I go the other way? Is it 4.45? Okay, so 4.45. So if I say 1 pound, that's the same as 4.45 newtons. Or I could have said 0.2248 pounds up here and 1 Newton down there, right? It would be the same thing. So
If that's 9.8 meters per second squared, why are we ignoring the square?
because that's part of the unit, it's not saying that the 9.8 is squared, it's saying that the seconds is squared, right? And it means 9.8 meters per second every second, right? Okay, and I struggled that with for like years before it finally dawned on me what the distinction was. So how many pounds is this? How many?
22.
22 pounds. Okay, so recognize that your weight in newtons is 4.45 times your weight in pounds. It's the same thing, it's just a different measure, right? So I weigh about 1,000 newtons, okay? That sounds worse than it actually is, doesn't it? So 22 pounds.
What is that in pounds?
Huh?
What is 1,000 newtons in pounds?
We'll divide it by 4.45.
Nice. Nice.
You can say what it is, I don't care.
224.
So actually I weigh a little more than that. So I weigh over 1,000 newtons. Marshall, you weigh over 1,000 newtons? Okay, but realize it's just a force. It's the force of the acceleration due to gravity pulling down on me. Okay? Now, your friend now pushes down on the box with a force of 40 newtons. Your friend now pushes down on the box with the force of 40 newtons. How would I add that into my free body diagram? Right now I've got the force due to gravity and I've got the normal force in the upward direction. How would I add my friend pushing down on the box into my free body diagram? Where would it go?
Would it go on the bottom as well?
Okay, so I'm just going to add it, right? I'm going to say force due to gravity and force normal. Or I'm sorry, not force normal, but we're going to call it a force applied. Okay, so I've got the force due to gravity and the normal force, or the force applied there. But is the box accelerating?
No.
So I still have to have a balancing normal force, but recognize it's now balancing both the force due to gravity plus the applied force, isn't it? And I always follow the same pattern of activity. Free body diagram, net force equation, and my net force equation here, am I accelerating or not?
No.
No. So what do I have to put that my net force equals?
0 newtons.
0 newtons. But now I've got a modified sum of forces, right? Now it's all of this minus that. So it's going to be force applied plus force due to gravity minus the normal force. And notice how doing this is tedious and it kind of sucks sometimes, but notice how doing this immediately provides me with a formula to find my answer. I want to know what the normal force is. Let's get this by itself because that's what my answer is, right? What am I going to do to the normal force to isolate it? I'm just going to add it to both sides of the equation, right? Normal force equals force applied plus force due to gravity. We already know what the force due to gravity is, right? We figured that out in the first part. That doesn't change. That's 98 newtons. And we've been told that the force applied is 40 newtons. 40 newtons plus 98 newtons equals 138 newtons. Okay? The whole purpose of the free body diagram is to allow you to create a net force equation, and the whole purpose of the net force equation is to allow you to create an equation that will solve your problem. Okay, I want you, using what we've talked about, to take a few minutes, let's say 4 minutes, and figure out what this would look like for this one. And you can talk with each other if you want. Okay, it's exactly analogous.
Would you be accelerating upwards though? Yes.
If I'm pulling up with a force of 40 newtons, is that going to overcome the force due to gravity?
Yeah.
So it's not.
No.
It's not.
So it'll still be no.
That's one of the questions that you have to answer, right? Is it accelerating because I'm pulling up instead of pushing down?
Normal force, and then you pull up.
Force.
Normal force is just going to be letters. Because
Or you are moving the box.
What do you think? What's the force due to gravity compared to the 40 newtons in the upward direction? Okay, so am I going to be accelerating in the upward direction if I pull upward on that box?
You're just gonna have a lower normal force.
Speculate that might be the case. Just follow the strategy. The strategy will lead you through the problem. Strategy never lies. Again, life is just a strategy. Or in the words of Jimmy Buffett, life is just a tire swing. Who's that? Never mind.
I know the name.
Do we have an answer? So some of you think it's 58 newtons?
yeah.
Okay, let's see if that's correct. Okay, so the uncertainty that I heard spoken from some of you was that you didn't know if this would actually cause. You're amazing, Bob. We already knew that.
Each one.
Thank you so much. You're awesome. Okay, so the confusion, or not confusion, but the uncertainty was that maybe the force that you're pulling upward on the box would cause the box to start moving. And that's not going to happen until what? That upward force is greater than the force due to gravity, right? So that's not going to happen until the force that I apply is greater than the force due to gravity. So, to answer your first question, it's not going to accelerate, it's not going to move, so I still need balanced forces, but this time, force due to gravity is all that's in the downward direction. But now I've got an applied force and a normal force in the upward direction. And I heard all of you come to the correct conclusion that all this is going to do is just make the normal force less. Okay? So we can confirm that net force equation, force net equals 0 newtons equals, and since the force applied is in the upward direction, the action is in the upward direction. Let's say that that's what's being put first, so the applied force plus the normal force. It doesn't matter, though. You could say this minus these two things, or you can say these two things minus the force due to gravity. Okay? But in this case, then, since I want the normal force, I'm just going to keep it on this side of the equation since it's already positive, and I'm going to say the normal force equals the force due to gravity minus the applied force.
I have a question.
Yeah.
So, is the normal force just the weight of the object on the surface?
Not always, because in this case, we've got somebody pulling up on it too, right? Now, but
Some weight off the surface?
absolutely. Okay, so, and we'll come to actually equate that. What we'll do eventually is we'll say, since I know that force normal equals, or the force due to gravity equals mg, I'll just, if it's balanced, I'll just say, well, this also has to be equal to mg. Okay? So at some point in our strategy building, we'll build that into it where we'll acknowledge just exactly what you said. But there will be cases where that's not true because of other forces that are acting on it. So you have to be careful when you do that. Okay? But again, what a great question.
Okay. But if it's an equal force on both sides, then it's going to be.
Yeah.
Okay, cool.
Yep. And that's a strategy point. We'll use that in our strategy in the future to help us. So 40 newtons equals 58 newtons, right? Okay. Okay, so we proved it. So and ultimately you could have just done that in your head, right? If you knew how this worked, you could have done that in your head, but you need to be able to prove it to me. Let me just make that a little clearer there. Okay? Yeah, you have to be able to show it to me. Again, we draw a free body diagram. The free body diagram informs the net force equation, and the net force equation informs the final equation that we use to solve our problem. Okay? Now, obviously, I could have put the force normal over here, and I mean, I don't really care how you arrange your variables as long as what it does is make sense. Okay? Okay, what happens to the normal force as different forces are applied to the box? What happens to the normal force as different forces are applied to the box? It changes. And this is a hallmark, and I'm just going to write this out here. This is a, oops. This is a hallmark of a reaction force. Okay? You know that Newton's third law is in action here if the force that you're working with changes depending on the circumstances. If I push down on this table with a tiny force, the normal force is also a tiny force. But if I push down on the table with a large force, the normal force becomes a large force. That force is changing depending on the circumstances, and that's the hallmark of a reaction force. Okay, so as some subtle points here, as gravity is pulling down on the box with a certain force, in this case 98 newtons, the reaction force to this is the box pulling up on the earth. Whoa, wait a minute, what? What did I just say? If gravity is pulling down on the box with a force of 98 newtons, and I just told you that the normal force is pushing up on the box with a force of 98 newtons, but now I'm saying, wait a minute, it's not that that's the reaction force. The normal force is a reaction force, but it's not the reaction force to the force due to gravity. Okay? It's a reaction force to my applied force. Now, think about this. Action-reaction forces have to be on the same objects. If the Earth is pulling down on the box has to be pulling up on the Earth. Yeah.
So if the applied force and the force due to gravity are equal, is there a normal force anymore, or would it equal 0?
The applied force and the...
So like if you pull up the box with 98 newtons of force, there's no normal force.
Absolutely.
Okay. Let's make it.
Yep, absolutely. Okay, there is no normal force. That's a really good question as well. But action-reaction forces are on the same objects. Okay? If I have gravity pulling down on a box, the box is pulling up on the Earth. What's the difference in that reaction force's ability to do something to the Earth compared to the box? Yeah, that 98 newtons affecting the Earth isn't going to do anything to the Earth. Now, theoretically, there's this tiny force of attraction that's pulling the Earth up. But it's not something we would ever be able to measure or notice, right? Okay, so regardless of how ridiculous it seems, that box that's being pulled down by the Earth with a 98 Newton force is literally pulling up on the Earth with a force of 98 newtons. As ridiculous as that seems, it's just that 98 Newton force on the Earth isn't going to cause it to do much, right? Okay. Now, however, because of its weight, this force of 98 newtons is also being applied to the top of the table. From the perspective of the table, this is an applied force. The box is exerting an applied force on the tabletop, which happens to be equal to the force due to gravity. Okay? That force on the box, that 98 Newton force due to gravity, is also being applied to the tabletop, and the normal force is the reaction force to this applied force. So there's two different sets of forces here, right? They just happen to involve one of the same objects. Okay? One set of forces involves the box and the Earth. The other set of forces involves the box and the tabletop. So the normal force is always a reaction force to an applied force, and that's why Katie's question was really a good question. If it's not the box that's applying the force, it's my hand. And in that case, it's not the weight of my hand, it's the actual force that I'm pushing down on the tabletop with. Okay? So the normal force is always a reaction force to an applied force, and sometimes the applied force is due to the force due to gravity, but the normal force is not the reaction force to the force due to gravity. As we can see, the force applied to the table surface can be modified by additional applied forces that are not the force due to gravity, and the normal force must adjust in response. Okay? So those are some really subtle points, and if you get that, you're doing really, really good, because that's not an understanding that a lot of high school students actually have. So I'm impressed by your understanding here. Now, just to make sure, weight versus mass. Mass is the amount of stuff an object has within it, the quantity of matter contained within the atoms and the materials making up the object. The amount of matter contained in an object is the same whether it's on the Earth, the Moon, 6 meters beneath the surface of the ocean, or in the cold depths of space. If the mass is an object that has 5.8 kilograms, that's its mass no matter where it is, unless it goes on a diet and loses some of that mass. Okay? But for all intents and purposes, the mass of an object doesn't change. Okay? The problem is we commonly use mass as a weight. When we go into the laboratory and we weigh something on a balance, we call it weighing the object. But if I find out that that object has a mass of 10 kilograms on that balance, that's not its weight, that is its mass. Okay? It's fairly common knowledge on Earth that 1 kilogram is equivalent to 2.2 pounds, so we become used to the idea that mass is the same thing as weight. But if you think about it, while 1 kilogram is mass, 1 kilogram of mass is still 1 kilogram, whether it's on the Earth or in outer space, while on Earth, this 1 kilogram mass has a weight of 2.2 pounds or 9.8 newtons, but in outer space it weighs nothing, right? That 1 kilogram mass is still 1 kilogram mass in outer space, but its weight is nothing, where on Earth its weight is either 2.2 pounds or 9.8 newtons. Now, in the metric system, it's easier to see that mass and weight are two different things. We multiply a mass of 1 kilogram by 9.8 meters per second and get the force due to gravity, or its weight. The problem is, in the English system, we don't have a unit of mass. We just have a unit of weight. Well, we don't seem to have a unit of mass. Nobody's ever told you about a unit of mass in the English system, have they? We actually do. And it's got a really interesting name. Somebody Google unit of mass in the English system.
Isn't it called the customary system?
What's that?
Isn't it the customary system?
I just call it the English system. I'm not familiar with the term customary system, but I'm willing to be taught.
It's like the one thing I remember from 4th grade.
4th grade, really?
Yeah.
The customary system.
Yeah, customary. Because customary, C-U-S for us, customary.
Okay. Okay. That's a good mnemonic. That's a good way to remember that.
I don't know why I remember that.
You got it, Jack?
Yeah, it says pound mass.
Okay.
Unit of mass in the English system.
Pound mass?
It says pound and then it says mass in both words.
Okay, that's not what I'm looking for.
Customary.
Standard's another word for English.
Did you come up with something different, Dexter?
I hope they
It says SICD or IUPN or LPN. Pound force or something like that.
do. Don't you mean koi story?
Okay.
Planetary imperial, see, that's another 153. It's not standard or imperial. No.
It's listed as pounds.
So let's,
Pounds now.
Look it up, it's
unit of mass in English system.
Okay.
Now, let's see if we can find out. Okay. The slug is the unit of mass in the U.S. customary system and the English imperial system. So the slug is the unit of mass in the English system. Okay, and the slug, let's see, how many, let's see. Slug is defined as the mass that is accelerated by 1 foot per second squared when a force of 1 pound is exerted on it. And in the SI system, it equals 14.6 kilograms. So 1 slug is 14.6 kilograms. Okay, but anyway, there is a unit of mass in the English system, or the U.S. customary system, as I've now learned. So I should modify my... Okay, so we actually do have a unit of mass if you're interested in looking it up. So we don't see this multiplication of mass by the acceleration due to gravity to get the weight. All we see is the unit of pounds. So if all I've ever known is a unit of pounds, it makes sense that I'm not used to converting mass to force or mass to weight by multiplying by the acceleration due to gravity. So anyway, to help us resolve this seeming contradiction, we can do a couple of things. One is focus on the idea that mass is a measure of how difficult it is to accelerate an object. Hopefully you've gotten that into your brain by now. That's Newton's first law. Mass is how difficult it is to accelerate an object. If I have a mass of 1 kilogram, it's a lot easier for me to accelerate that mass than if I have a mass of 10 kilograms or 100 kilograms. So focus on that idea. Mass is a measure of how difficult it is to accelerate an object. The greater the mass, the more resistance to being accelerated. This resistance being accelerated is the same no matter where the object is. If I'm on a frictionless surface standing on the Earth, it would take the same amount of force to accelerate me in a horizontal direction as if I was floating in outer space. The other thing you can do is simply think of mass as being multiplied by a constant to get the weight, and the value of the constant changes depending on where you are related to a gravitational body. Also understand, gravity only affects how difficult it is to accelerate a mass if part of the motion is in the same direction as the force due to gravity. If motion is completely in the horizontal direction, the force due to gravity doesn't affect how difficult it is to accelerate something, unless there's a force due to friction. So if we're on a frictionless surface again, if I'm on a frictionless surface, the force due to gravity doesn't affect how difficult it is to push me from side to side. That force due to gravity only comes into play if I'm being also moved in an upward direction or a downward direction. Okay? So there's a lot of subtle points there, and we need to consider all of those. Okay, so I'm going to pass out. You want to just send those around? Oh, give me one. Thank you. We're just going to look at a couple of questions here, and then we'll stop.
I don't think I have that figure. That's why.
Okay, has everybody got one of these? And I'm not going to ask you to hand this in today, but we will work on this for a couple of periods here. Which of Newton's laws best explains why motorists should buckle up? Bless you. Which of Newton's laws explains why motors should buckle up? All of them?
Second.
First one.
Why the first one?
That's one with inertia.
Okay, that's the one with inertia. It's hard to change my motion, right? If I'm going the same speed as the car is, but then the car stops, it's hard to change my motion. My motion's not going to change. I'm going to keep going, right? That's Newton's first law. You can't change my motion unless you apply a net force. And the net force that would be applied would be the steering wheel and the windshield, right? That's why you should put your seatbelt on. If your car comes to a stop, you don't. Okay? That's also a problem for not only your skull, but actually I've got a diagram of a heart up here, don't I? Look at the heart right here. See these three blood vessels? Okay, see these three blood vessels right here. They're tethered to the inside of your body. They're kind of stuck to the inside of your body. And when your car stops, when your body stops, these blood-filled vessels keep going. Okay, so if you hit a tree going 30 or 40 miles an hour, you're going to die instantly because, or at least you're going to not feel anything anymore instantly because your aorta is going to rip, because the aorta is going to keep going, but where it's attached to your body is going to stop, and your aorta will rip. You will bleed out immediately. Your blood pressure will drop to 0 immediately, and you'll pass out and you'll die. Okay? That's why you should wear your seatbelts.
I would live with it because it's
Okay? Seatbelts are kind of like masks, aren't they? Masks are the seatbelts of the 2020s, right? Okay, when you sit on a chair, the resultant force on you, the net force on you is what?
Yes.
What's the net force on you when you sit on a chair? Why? Because you're not accelerating. Good job, guys. I'm really impressed in how quickly you've caught on to this. If there is no acceleration, your net force is 0.
What's the definition of resultant force?
It's a net force. The resultant, and it's also another term for the sum of forces.
okay.
Okay? Sum of forces, net force, it's all the same thing. In the absence of an external force, an object will...
Oh, I just circled 2.
In the absence of an external force, a moving object will... Thank you, move with the constant velocity. Our experience is that if I stop pushing on something, it slows down and comes to a stop, right? But there's a net force on it, right? Friction is acting on it. But if there is no external force acting on it, I don't know why they came up with some stupid name for this spaceship, But when the rocket engines on the Starship No Pain, No Gain are suddenly turned off while traveling in outer space, the Starship will immediately, or will move with a constant speed. A rocket moves through empty space in a straight line with a constant speed. It's far from the gravitational effects of any star or planet. Under these conditions, the force that must be applied to the rocket in order to sustain its motion is zero. Okay, now, whose philosophy would be that in order to keep it moving, I have to continue to apply force? Would that be Aristotle's philosophy or Galileo's philosophy? Aristotle thought that you had to continue to supply a force, right? Okay, but Galileo said, no, we're in constant motion, even if it's a constant motion of zero, and I only have to apply a net force if I want to change its motion. But if I'm going in a constant motion, I don't have to apply any force to keep it going. You're standing in a moving bus facing forward and you suddenly fall forward. You can imply from this that the bus is A, velocity decreased. Right? Again, Newton's first law, right? I'm going to keep going. The bus stopped, but I'm going to keep going. Okay? Now, you suddenly fall forward as the bus comes to an immediate stop. What force caused you to come to a stop or fall forward? What force caused you to fall forward? If I'm moving, the implication is there must be or if I'm suddenly moving, the implication must be that there's a force. There's not a force, right? You just kept going in your constant motion. Okay, that one was a little trickier, wasn't it? But it still makes sense, right? Right, Beckham? Okay, there wasn't a force. A constant net force acts on an object. Don't get confused by the word constant here. Constant's not referring to velocity, is it? It's referring to a force. There's a constant net force. Describe the motion of the object. If I say that I have a constant net force, that means I have a non-zero force, net force acting on me. That means I must be doing what? I must be accelerating, right? But because this force is constant, it would be a constant acceleration. Right?
So can you not have a constant net force of zero?
Okay, that's the problem with this question. It ignores the fact that you could have a constant net force, but the term net force implies that it's non-zero. Okay? But it's not very clear about that, is it? Okay? So I would never give you language on a test question that would do that to you. Okay? It will always be clear whether the force I'm talking about is 0 newtons or not 0 newtons. Okay?
You can have a constant net force of zero.
Yes. Okay? So, bad question, right? I'm glad you recognize that. Okay, we know that since force equals ma, that A equals force divided by m. So the acceleration of an object is inversely proportional to what? The acceleration is inversely proportional to mass, right? If I increase the mass, I decrease my acceleration. If I increase the mass, I decrease the acceleration. If I decrease the mass, I increase the acceleration, right? A net force F accelerates mass m with an acceleration of a. Okay? This is a what if I change a variable question. This is a what if I change a variable question, what happens to something else? And if I have a what if I change a variable question, I always write out the formula that answers that question. I know that acceleration equals force divided by mass. And then I say, well, what variable am I changing? I'm changing the mass here, right? What if I change mass to 2m? What do I do to the acceleration?
Multiply it by 2.
It's also going to be divided by 2, right? If I change the right side of the equation by dividing it by 2, I have to divide the left side of the equation by dividing it by 2. So if I double the mass, I have the acceleration. Okay? Same kind of question here on 11. A net force F acts on mass and produces an acceleration. What acceleration results if a net force 2F acts on a mass 4m? Now I'm changing both of these, right? So what I'm going to do is I'm going to write out my equation again, and I'm going to see visually what happens to both of these things. I'm going to put 2 in front of that, and I'm going to put 4 in front of that. What happens to my acceleration?
Same thing.
Same thing, right? This is multiplying the right side of the equation by 1/2. So I'm going to multiply the left side of the equation by 1/2 as well, or that would be a over 2. Okay, we're going to stop there. How quickly did we go through 11 reasonably difficult conceptual questions? Okay, is this making sense? And if it's not, what can I do to clear it up? Or is it making some sense? Okay? Marshall accomplished teaching something today. You guys are awesome. Thanks for your attention.
You're welcome. You want that?
No, we're going to keep working on it. And I've got too many papers to deal with that right now.